If you want to understand how we can predict outcomes based on the data by using patterns and similarities, this video is for you. Today you will learn how the k-nearest neighbors algorithm works, a simple yet powerful way to solve classification and regression problems. Let's dive in. The k-nearest neighbors, or KNN, algorithm is a simple but effective way to predict outcome based on the similarity to other known data. It's based on the assumption that if the new object is located near or surrounded by others similar objects, it likely shares similar features. This applies to both classification problems, where we assign the category to new data, or regression problems, where we estimate a continuous value based on the surrounding data. Since KNN relies on the dataset with known labels, it falls into category of supervised machine learning. We can imagine a set of points on a plane where each one is described by two features placed on the x and y axis. Each point is assigned to one of two categories, A or B. The division is not random. It's based on the similarity of features and proximity in the space where the point exists. I use the terms similarity and proximity interchangeable here because x and y don't have to represent physical dimensions like length or width. They can be any features, and their interpretation depends on the problem being addressed. But what category should we assign to the new point that we haven't encountered before? The KNN algorithms give us a guideline. It says, select the k nearest neighbors and assign the category that is the most common among them. This method requires us to calculate the distance between the new point and every point for which we already know the label. How do we calculate the distance between 2 points? Assuming we use the Euclidean metric, the one we intuitively use in the everyday life, we should apply a well-known formula. In our case, the distance is calculated as a square root of the sum of the squared differences between the corresponding coordinates of 2 points. I know it sounds complicated, but it's easier to understand when you look at the equation above the graph. Not every problem boils down to 2 independent variables. That's why I'm showing the general formula for calculating the distance between 2 points, P and Q. However, it's worth noting that other metrics exist, and for some problems they may be more convenient to use. An example is the Manhattan distance, which better describes the distance traveled by vehicles in city, restricted to parallel and perpendicular streets. Once we have calculated the distances to all points, we should now limit ourselves to nearest few, whose labels we already know. The number of these points is typically denoted by the letter k, which is the part of the algorithm's name. If we choose k to be, for example, 4, we select exactly that many closest neighbors and then use them to predict the label of the new data, whether it's category or continuous value. If you are not quite grasping the idea behind the algorithm yet, it will become clear once we start implementing in Python. So let's jump into Visual Studio Code. We will now move to the coding environment and begin by importing a few essential modules, math, statistics, and the counter data structure from the collection module. Math and statistics provide us with tools for performing standard mathematical operations. Let's take a moment to focus on the counter class. It is essentially a dictionary that, when created from the sequence, stores unique elements as keys, and the value for each key is the count of how many times it appeared in the original list. Before we move on to implementing the KNN algorithm, we will create two functions using matplotlib library to visualize our data on the graph. First, we import the necessary module. The first function, plot classification, will take in training data, training labels, and test point. We'll start by creating a dictionary that maps categories to the graph colors. Next, we'll prepare for list for x and y coordinates, 2 for each category A and B. We will iterate through the training data, the known points and their labels, unpacking them into prepared list and displaying them on the graph in the appropriate color of the category. Finally, we will add the test point to the graph with a different marker and color chosen based on its predicted category. We will add also labels, a title, a grid, and legend to the graph. The second function, plot regression, will be quite similar in structure. However, the graph will be different because the color palette will be representing predicted value of the feature based on the KNN algorithm. We will begin by defining its parameters and normalizing the range of values in the training data. Next, we will plot the points with the color scale corresponding to their normalized values. We will also plot the test point representing the prediction. Of course, its value must be also normalized. Finally, we will describe the graph with axis labels, a title, a grid, and legend. With the helper function prepared, we can also move on to the KNN algorithm itself. We will start by defining Euclidean distance function, which calculates the distance between 2 points. This is an implementation on previously discussed formula. Next, we will prepare training data for both classification and regression problem and define the parameter k as a tree, representing the number of nearest neighbors involved in making prediction. For the classification problem, we will create KNN classifier predict function. It takes training points, training labels, a test point, and the k parameter as argument to return predicted category for the test point. The first step is to calculate the distance from the test point to each training point. We will store these distances along with the training points labels as a tuples and add them to distances list. Next, we sort that list using sort method and lambda expression. The goal is to keep the k shortest distances along with their labels. In the final step, we extract only the labels into a list. Then create counter object and use its method most common. This returns the most frequent key value pairs, in our case the most frequent labels. Since the result is returned in a specific format, we access the key using additional indices 0, 0. We then return this value as a predicted category for the test point. Now we can predict the label for the test point with coordinates 5, 5, and then plot all the data on the graph. As you can see, category B is assigned, even though it's just slightly closer to that group of points. For the regression problem, we'll create the KNN regressor predict function, which is very similar to the one used for classification. The only difference is that instead of predicting labels A or B, we'll predict the continuous values. Once we have the k closest value to the test point, we can determine the predicted value. Unlike the classification problem, we calculate average of these values instead of trying to select the most frequent one. Once again, we'll present all the data and prediction for the test point with coordinates 5, 5 on the graph. This time, the graph looks a bit different because the color of the points represents their values, normalized to range from 0 to 1. We have covered the theory and implementation of KNN algorithm for both classification and regression problem. Now, I would like to show you how to use ready-made tools that perform the same tasks. These are available in machine learning library scikit-learn. Let's start by importing two models. For the classification problem, we need to create a model object with the chosen parameter k and then train it on the training data and labels using the fit method. To make prediction for the test point, use the predict method, providing the test data as a list. In our case, it will be single element list, though the method can handle multiple entries at once. The graph shows the result that we have already seen. We approach the regression problem similarly. We create an object of second model we imported, then train it on the training data and values using the fit method. We make prediction the same way as for the classification model. We pass the test point to the predict method, which returns the predicted value. After that, we again visualize the data on the graph. I hope this video helped you better understand how the k-nearest neighbors algorithm works. We covered its concepts, implementation, and practical use. Along the way, we also had a chance to get more familiar with the scikit-learn library, which will certainly make more appearance on this channel. If you have any questions or would like to see more examples, feel free to leave a comment. Thanks for watching and see you in the next video.